Hello, and welcome to the introductory video of a course which I've entitled Introduction to the Theory of Semiconductor Devices. The course is about 50 hours of video instruction spread over 46 sessions. I'll be your guide. My name is Joel, and the material covers more or less the material that one would cover in a first course in semiconductor devices. There is an online text which I've been writing for the last 4 or 5 years or so, and I've entitled this A Companion Guide to Semiconductor Devices. And I entitled it Companion Guide because I like to think, at least, that it's compatible with most of the main textbooks in either undergraduate or graduate instruction for this particular subject. There are a few advanced topics in the text which we will not be covering in our video courses, things like a probabilistic approach to the Fermi-Dirac function, block functions, and quantum theory, the Bardeen theory, and one more, the Shockley-Hall-Reed theory. So those are marked with asterisks, and we will not be particularly covering them, but they're covered in the text. The text is a bit long-winded. One of the reasons is that all of the equations are derived, and they're derived in rather gory detail. So that creates a lot of pages. Anyway, so to receive a copy of the text and the session handouts and the summaries, which will be given from time to time, as well as for your questions, you can email me at this email address right here. Your questions, your comments are always welcome. I just have two requests. Things that I don't like are, one, effusive praise. Fortunately, I get very little of that. And comments which are derogatory or, see if you can cut down the 4-letter words if you don't like things. So this is kind of a summary of what we'll be doing. There are 24 chapters. We'll start out with an introductory chapter, which includes relatively little mathematics. Trying to emphasize the idea of units, and you'll see how that goes in Chapter 1. Chapter 2 is semiconductor properties, optical properties, band gaps, lattice structure, things like that. Chapters 3 and 4 involved semiconductors in equilibrium. There are 1 or 2 advanced topics here. As I said, we won't be covering. Those are covered generally in appendices. Some basic quantum theory is covered in Chapter 5, and Chapter 6 and 7 we cover semiconductors in non-equilibrium. Chapter 6 is basically work problems for the first 5 chapters, and then Chapter 7 we get into non-equilibrium. And then we have what I like to call the device structure tree. And then we get into devices which are composed of 2 or more different semiconductors. And central to this theory, or the first thing that we cover, which is a little bit unusual in courses, generally one starts with p-n junctions. I prefer to start with the metal semiconductor. It has to be all of these involved, either 2 layers or 3 layers. So we start with a 2-layer structure, a metal which is in intimate contact with a semiconductor, and that's called the Schottky barrier or the Schottky junction, and that is covered in chapters 8 to 10. Chapter 8 is the basic theory in equilibrium. Chapter 9 is the non-equilibrium or the bias of Schottky junction, and Chapter 10 involves worked problems. And then we go down the left side of the device structure tree, where we replace the metal with another form of semiconductor, and we look at a p-n junction, and that is covered in chapters 11 to 13. 11, again, equilibrium, 12, non-equilibrium, 13, worked problems. And then we add another junction, so we have 3 separate semiconductor materials with 2 junctions in the middle, and that is called a bipolar junction transistor, or BJT, and that is covered in chapters 14 to 16. Again, it's a little boring. 14, equilibrium, 15, non-equilibrium, and 16, worked problems. Along the way, on the left side of the device structure tree, we cover some non-traditional kinds of devices, specifically the PIN junction, or the PIN diode, and the ISO junction. And in the BJT chapters, we cover, specifically chapter 15, we cover the heterojunction, bipolar junction transistor. And then we make this big leap to the right side of the device structure tree, where we take the metal semiconductor and we stick in a layer of glass, of oxide, silicon dioxide. So the metal oxide semiconductor, also called the MOS cap, is basically just the metal semiconductor with an oxide in the middle. Now, we could have gone directly, that's why I have this dotted arrow, but I prefer to go kind of roundabout and then go back. So we have a little bit of review of the metal semiconductor before we get into the MOS cap, and that is covered again in 3 chapters: equilibrium, chapter 18, non-equilibrium, and chapter 19, worked problems. And then we finally get into the MOSFET, the MOS field effect transistor. That is covered in chapters 20 to 23, equilibrium, non-equilibrium, and then a chapter on short channel effects, and finally chapter 23 is worked problems. Actually, there's 2 chapters in short channel effects, chapters 21 and 22. And then finally we end with a chapter on novel structures, and we take the energy band diagram and go over some general rules for drawing energy band diagrams, and we use those rules to talk about the high electron mobility transistor, the HEMT. So that's the course, and if you find it interesting, welcome aboard, and we're glad to have you.